Hello everyone, I'm Feng, now an assistant professor of marketing at Zhejiang University, as well as a research fellow of Wharton Neuroscience Initiative. Today I'm going to talk about how we can detect a prevalent bias in decision making, loss aversion, from our eye activity. Loss and gain have different impacts on our decisions. Loss aversion describes our tendency to prefer avoiding losses to acquiring equivalents or larger gains in decision making. For example, just imagine you are presented with a gamble, in which winning and losing is determined by flipping a coin. If the coin lands with heads, you win $120, and if it lands with tails, you lose $100. That is, in this gamble, you have equal chance to win and lose money, but the potential gain is larger than potential loss. Will you accept gamble or reject gamble? According to traditional economic theory like expect value theory, you should accept gamble because the expect value of the gamble is larger than zero. But researchers found that most people actually rejected such a gamble unless the magnitude of gain was much larger than loss, like twice of loss. This phenomenon was first observed by the two founders of behavioral economics, Kahneman and Amos-Tversky. Kahneman later won Nobel Prize in economics, and he considers the concept of loss aversion as their most useful contribution to the study of decision making. But an unresolved question is why people make loss-averse decisions. There are different explanations. Here I focus on two of them. First, Kahneman and Tversky conceptualize loss aversion as a valuation bias. They assume that when people evaluate potential gain and loss, they overweigh loss relative to gain. Consequently, even when the amount of gain is larger than loss, after weighting, people may still feel potential loss is larger than potential gain. By contrast, an alternative will argue that it's not about valuation bias toward the loss or gain, but about response bias toward accepting or rejecting gambles. According to this view, people have an initial response tendency to reject gamble, which is irrelevant to the amount of gain and loss. Because once you accept a gamble, you will have the possibility of losing money. But if you reject it, you can totally avoid the possibility of losing money. Both of the two accounts can explain why people reject gambles of positive expected value. And only based on observed choices, it's hard to distinguish the two accounts. So is there any way that we can reconcile the two accounts? My colleagues and I at Wharton developed a computational model for the gambling task to incorporate both of the two accounts. We assume that the decision of accepting or rejecting a mixed gamble is a noisy evidence accumulation process. Here, the x-axis is time and the y-axis is relative decision value. In the decision process, the relative decision value moves toward the bottom or up boundaries. When it reaches the bottom boundary, the gamble is to be rejected, and when it reaches the up boundary, the gamble is to be accepted. Then what determines the velocity of the process? That's the relative size of gain and loss. When gain is much larger than loss, it tends to move up, and when loss is much larger than gain, it tends to move down. And the coefficients for gain and loss represent their relative weights in the velocity. Accordingly, the ratio of the two coefficients indicates the size of valuation bias. Then where is the response bias? It is indicated by the starting points of the process. When the starting point is right in the middle of the two boundaries, it means no initial bias for the two response. But when the starting point is closer to the bottom boundary, it means there is an initial bias to reject gambles. We can formulate the size of response bias as its distance from the middle point. So by doing this, the model accommodates both valuation bias and response bias in the computational process model. Moreover, based on this model, we further predict that the two biases can be observed in gaze allocation and pupil dilation in the decision process. Gaze allocation often reflects our evaluation bias. For example, research found that when males judge the attractiveness of two female faces, they tended to look more at the face they finally chosen. Similarly, research found that when consumers make purchase decisions, if they look more on the products, they probably will buy, but if they look more at the price, they probably won't buy. So go back to our gambling task. We hypothesize that people overweight loss probably because they look more at loss than gain in the decision process. In short, we predict that gaze bias toward loss is related to valuation bias toward loss. Next, pupil. Pupil dilation has been related to many different psychological processes, like surprise, fear, belief updating, and working memory. A recent convergent view is that pupil dilation reflects mental efforts. That is, when your mind is working hard, the pupil is dilated. Surprise, fear, belief updating, and working memory all imply much mental effort. So in our framework, if there is a response bias to reject gambles, we would predict that accepting a gamble would be a more active decision process than rejecting gamble. Thus, we would expect to observe larger pupil dilations when gambles are being accepted than when the gambles are being rejected. In short, we predict pupil dilation in decision making is related to response bias. This is a summary of our framework. We assume that loss variance can be decomposed into a valuation bias and a response bias, which can be formulated in a computational model. And valuation bias is related to gaze allocation to loss and gain, and response bias is related to pupil dilation to accepting and rejecting gambles. We tested our hypothesis in an eye-checking experiment. Participants were presented with 100 gambles of equal chance to win and lose money. For each gamble, they pressed one or two keys to accept or reject it. This is one example. The left is potential gain and the right is potential loss. There are 100 different gambles in total. We recorded participants' choice and response time for each gamble. Then we can fit our model with observed choice and response time data to identify each participant's valuation bias and response bias. We found that most participants showed both valuation bias and response bias. Next, let's see whether the two biases can be identified from gaze allocation and pupil dilation. This heat map shows the probability of gaze allocation on the screen. The brighter a pixel is, the higher probability it is fixated at. We can see that the loss region is slightly brighter than the gain region, which suggests a gaze bias toward loss. A question is this gaze bias related to these decisions? Yes, we found a negative correlation between gaze bias toward loss and probability of acceptance. Participants who spent more time looking at the loss also accepted fewer gambles. Next, we would like to know whether this gaze bias reflects valuation bias or response bias. As predicted, we found that gaze bias is mainly associated with valuation bias, not response bias. Next, pupil. We predict that when there is a response bias to reject gambles, accepting gambles would be effortful and thus dilate pupil. As predicted, we found that when gambles were being accepted relative to being rejected, participants showed larger pupil dilation. Moreover, we found a negative correlation between probability of acceptance and differential pupil dilation to accept and reject gambles. That is, participants who tend to reject gambles showed larger pupil dilations when they accepted a gamble. Finally, we would like to know whether this pupil dilation reflects valuation bias or response bias. We found that larger pupil dilation to accepting gambles mainly reflect response bias, but not valuation bias. So our results confirm our framework. Our findings have important practical implications. In our study, we show that gaze allocation can impact loss aversion. Consequently, we would predict that manipulating gaze allocation may change loss value. And one simple way to manipulate gaze allocation is to change the view salience of gain and loss. For example, making the gain's font size larger than loss, or making the loss font size larger than gain. We tested our hypothesis in a follow-up experiment. We found that when gain font size is larger, participants accept more gambles, and when loss font size is larger, participants rejected more gambles. And nowadays, we know that consumer finance apps can easily change the font size of gain and loss or revenue and costs on their apps. So if a consumer finance app displays gain with a larger font size than loss, it can tempt consumers to make more risky decisions. This may involve many issues we can discuss. Okay, this is my talk today. Thank you, everyone.